What's up, everybody? How are we doing today? I see we got Ivan here, Trace here, William here, Ben here, Dylan here. How's everyone doing? Like, our officer was about to start here in 1 minute. Yes, they are. Had a little bit of lunch. Doing good. I need to get that second cup of coffee in me. Woo, coffee. Oh, man, I love coffee. See, we got some questions starting up here on 2A. I don't know if it was just me, but it said office hours would start in an hour. Oh, did it say office hours would start in an hour? Oops, that's my fault. Maybe there's another video. Maybe I put the wrong time on this one. I do that every once in a while. Yeah, at 3. Well, then that's my mistake. Sorry, everyone. Oh, it always does? I must have copy pasted the wrong time. Maybe it didn't used to do that. Maybe no, that looks to be my mistake. Sorry about that. It always does? Well, whoops. That's, you know, Knoxville, I don't know time zones. That's my excuse. Sorry about that, everyone. Sorry about that. I didn't know that. Everyone, a question about the check regression function, the hamster limb shall test. I'm running the code over and it gives me a different value. Yep. And don't worry, I've got a huge boundary when we run your results. So it's a very nice boundary, and I look at it. How would I know which one to choose? It uses randomness to do it, so it's all right to run it one time. I think, do I say to use a set seed on it? If you use a set seed, you'll get the same result. Generally use 320 set seed. I'm trying to think if I said that, but also I put some niceness in there. I think one of those does have an issue. So use 320 set seed. That'll keep your randomness the same. Run the set seed 320. Your randomness will be the same, and just keep it to that. But I do some niceness if there's any sort of randomness to make sure. And I look at, like, if you say the p-value is 0.80 and the p-value comes back 0.008 or 0.09, then there would be a big difference right there, Aisha. Does that make sense? So, yep, Aisha, awesome. So I make sure, I'll look over that to make sure no one loses points who is like, if due to any randomness. We don't want that randomness losing our points for us right there. So let's take a look. I think 2A and 2B were questions. You're welcome, Aisha. Thank you for being here, and thank you for asking the questions. Ivan had a question over 2A and 2B. So let me go get the assignment up. I was going to show everyone something. I'll show this really, really quick. Really, really small thing right here. You ready? Let's go over to it real quick. So something I was going to show right here, but I got sidetracked when we talk about 475, is you're going to start by creating the app right here. I need to blank the screen for 1 second because I need to go select the file. This is with the app creation. Now, I wrote a lot of this code right here. I used part of this code's mine. Part of this code is what I found online because like I had to create all the pages and stuff. But I basically am giving people this template to use where you can go through here and investigate data. So this is actually being run in R. So if you're thinking about 474, 475, this is 475 actually. You'll be working with this right here, this sort of build I made where you can select your X and Y variables. And we're kind of starting off the basics. But I give you this basically 100 lines of code right here that then you can utilize in your Shiny apps to then create your own kind of Shiny apps with it, to where you can run the app, you can load in the data, and your first group assignment will be kind of going over this and building things here, building pages, and making your own apps to analyze data. I've got my own app, and let me show you that really quick. Where's my regression app on here? Because if you want to see something, I'll show you. It doesn't do logistic. It doesn't do logistic. I need to go to recents then, and then we're going to do assignments. Recent files, regression latest. Okay. So this is my regression solver right here. I'll show it to you in 2 seconds. It's 342 lines of code. So this is a regression solver I built with 342 lines of code. Let's run the app. So here it is right here, regression modeler 1.0. I did the set seed and it still ran. Yeah, if you see any issues with the grading, tell me. It shouldn't be any issues. Shouldn't be any issues. I want to show you right here, and I worked really hard on this to make this, but check this out. I loaded in the data right here, and then I can go here to investigate data. And you know what function this is in the background right now? Who has any idea what function is running in the background right here for you? Does anyone have any idea what function is running in the background if you select like desired weight, and it's giving you all of this right here sorted? It's also highlighting the values that are statistically significant. The Kahoot in Eastern, I think, is 5:30 Eastern. Double check, the video should be posted to the YouTube channel. It should be 5:30 Eastern. What function is running in the background right here? And you can see it. All correlations, Dylan. Yep, this is running all correlations. and it's telling you what is statistically significant. I wanted to make it so you could click the variable and then it would come up as the X. I couldn't figure that out, but I was able to color code the rows here to give you all correlations. And so I actually had to recalibrate all correlations. But when you select a variable, it literally does the all correlation for you. And you can search through and find certain values. So you could type that in right there and it'll literally find values. It's so neat what you can do with this. And what you can do here is you can select another variable and you could go over here to the distribution and see the Y distribution of the variables. And these are all being done in Plotly. So you got hover abilities and zoom in abilities if you want. You can go to the scatter plot and get the fitted line. And if you don't want the smooth line, you can just click away from that. I think it's really cool too. And this is kind of what we're starting out with. I don't expect people, I think the check regression still broke. No, check regression works. Okay. I think for some it doesn't work though. Check regression is working right here, and the model summary is created. So you've got your model summary, you've got your check regression, you've got your scatter plot, you've got your distribution of the two single variables. You can investigate relationships right here. And just as you change this, it changes to what you're talking about. So you can see that one is very skewed. We probably fail some check regressions on this now. Normality of the residuals is going to fail. And I couldn't get the plots to appear here. I was trying to get that also. You can see there's a little bit of nonlinear relationship. But anyways, this little thing I built right here is built on what I'll be asking students to do. I don't expect students to do this amount of work. And it looks like it was running my check regressions in the background there. So I don't expect students to do something that crazy. What you're going to do in 475 to start is take a statistics 201 or 320 concept and build something like this. You're going to work on a team, and you're not meant to solve all the problems in the world. You're meant to understand Shiny and start utilizing these topics that we'll be talking about the first week of class. So enough about new classes. Let's talk about your class. So I saw the question originally, and feel free to put more questions in the chat. Can you go over 2A and 2B interpretations? Let's go over question number 10, logistic, and let's hop into it. Here we go. 8 minutes in, we're on topic. Here we go. Brian, my LM for assignment 10 won't show anything S-curve. Make sure to not use LM. What are we using for assignment 10? And make sure to don't use the things I'm using right here. What are we using for assignment 10? No longer LM. No longer LM. No more LM. LM is gone. GLM, you're right there. Create a multiple. Oh my God. It is logistic. Everything here is logistic. And I do use GLM. Send it to me on Discord, Trace. Send it to me on Discord. So Discord it to me. And let's take a look right here. Let's take a look. Q set, exactly. So remember, don't use my models. Don't use the ones I do. I'd try to stay away from predicting gender. That's the one I always predict. It's just the easy one. It's the one that is in all my examples. So we want one categorical. And really, you're kind of stuck with this data set. You probably want to go outside of Survey 10 because Survey 10 only has in it 2 categorical variables, unless you discretize another variable, which means to make discrete. And the important thing with GLM is to go right here. Now, it does say a categorical Y. You'll analyze multiple logistic regression fully. Here you go, quantitative X and well, this isn't the latest version. Wait. Am I just going mad? I swear I updated this and then... Oh, we don't have to worry about that, William. Everyone, I'm just going mad right here. 2 seconds. Let me take a look at this. Let me see what the latest... Brian's lost his mind, everybody. Okay, assignment 10's posted. Let me download the latest version. Well, I'm going to have to be very nice in the grading at this point. I'm going to be very nice in the grading at this point because I obviously have more errors in this than I would like. But it still says V2, yeah. I don't know. This is what happens when Brian's brain overheats, apparently. On Discord, stars a fly. It is logistic. Please make sure you're doing logistic. I'm going to have to be a little bit nice on the grading on this. Nicer than I would like to be. As in, I'm probably going to have to give someone points if they're not following the instructions properly. At least the intended instructions. So please do logistic. It's going to majorly help you for the test. If you don't know how to interpret logistic, it's going to majorly hurt your test grade. This is all logistic, hence why the assignment's named logistic, hence why it says multiple logistic. Logistic has a categorical Y, and let's go down, run that code up here. Here we go, let's grab this code, and the intent is that. That's the intent. Now, and we don't want the interaction yet. Why is this called logistic? Why is this called logistic? It's pretty easy right here. Why is it called a sigmoidal curve? That's about one of the easiest questions I could ever ask you. Why is it called a sigmoidal curve? Why is it called a sigmoidal curve? Why is it called a sigmoidal curve? About one of the easiest questions I could ever ask you. A lot of kind of basic understanding questions right here. Why is it called a sigmoidal curve? Yeah, exactly. The sigmoidal curve bounds it between 0 and 1, and that's the S shape it has. So it has an S shape. Sometimes it might be hard to see, especially if you're looking at a tighter boundary. And Dylan, I can take a look. Thank you so much, Dylan. I'll take a look at that here in a second. Look at the graphic and explain why you can't interpret the coefficients. Why do the coefficients, exactly like we do not mention the value of the coefficient, we cannot mention the numeric value of the coefficient. This is a huge thing we need to know, and I was trying to drop major important things right here. Why can you not interpret this value right here? We will interpret the sign of the coefficient, but why can you not interpret this value of the coefficient right here? Why can you not interpret this value of the coefficient right here? Why can that value not be interpreted? Why can that value of logistic not be interpreted? And we're not going to say like are expected to differ by a probability of 0.70. It's not constant. The differences in probability, the only thing that matters here is the what of this, which you see there's nothing there. So what is the only thing that matters? Nonlinearity, exactly. Great answers on top of it right here, exactly. And the only thing that matters about this coefficients is its what, just like these coefficients right here. These have interesting interpretations. I'm going to interpret these here in a moment, which really gets into, I think, question 2 or so. So what is the level of interest in your logistic? Yep. Level of interest is pretty easy to see if you visualize. So I will say this, level of interest in your logistic is what comes last, and it's always going to be right here on the graphic if you can visualize it. So I said some pareidolia. I thought I saw someone. What? If you hear me scream, remember. I'm losing my mind. So what is the only thing we interpret right here? What is the only important thing you interpret when you do this right here? What is the only important thing you interpret? The only important thing you interpret is what? No one said it yet. The only important thing you interpret is the what of the coefficients. And we can see it right here. This is an interesting one with the categorical variables. The sign of the variable, exactly. The sign is the only thing we interpret. All of this is sigmoidal up or pulls it in the positive direction. So two individuals who are otherwise identical but differ in their height by 1 inch. The individual who is taller is more likely to be male. Two individuals who are otherwise identical but differ in their height by 1 inch. The individual who is taller is more likely to be male. Now, if you notice right here, the reference line is the black line. And just think about this. If we have otherwise identical individuals, but a person is left-handed versus an ambidextrous person, the left-handed person is what likely to be male, which is weird, and it's not statistically significant. But the person who is left-handed is what likely to be male compared to the person who's ambidextrous. Ambidextrous is the black line, it's the lower line, and the person who is left-handed, right here has a what probability of being male at all times to the ambidextrous person. As in two people who are otherwise identical have the same height, but one person is ambidextrous and the other person is left-handed. The person who is left-handed is more likely to be male. It's ridiculous, and it's not statistically significant, as shown by the drop 1 test. So we talked about this last class, especially that when you're over here, it should be chi squared, and it wants a capital chi squared. The capital chi-squared right here runs the test and tells you that handedness is not statistically significant. As in, we are comparing a model with handedness and a model without handedness. And we're looking to see if handedness helps us out and changes from the null deviance, to be specific right here. Like, we're in this regression, we're no longer looking at sums of squared error, so we can't look at reduction in sums of squared error. We can look at change in null deviance. So this does not actually help it. And that's probably the best way to explain it to someone, is to just say, handedness is really not doing much for us. It's not helping us out right here, and this can be especially seen. This is an effects text, correct? Yep. Great answer right there, Trace. 100. Why not 100 points? Why not? Thank you for everyone for being here. It's the end of the semester. 100 points on these Mega Mondays. What up? So that literally tests the effect of handedness. And we might, does it say that when we do the visual? Yeah, here it is. There's the p-value right there. Boom. It just gives it, just get it right there also. So you don't even need to do the drop one. It just does it for you right there. And so Trace, great review on that. That is the effect of handedness. As in, when we look at a model with handedness and a model without handedness, then we get this effect right here. The total impact of the removal of that variable to see if that variable actually helps our model. Does it reduce the sums of squared error, or does it help the null deviance? Null deviance will not really, I don't even mention it on the test, I don't think. So how's that looking right here? Is this making sense? As I explain these coefficients, this kind of got into a little bit of number 2 right here, where I'm talking about how to explain the coefficients for individuals. Would you please, let me take a look. Yeah, here we go. Let me take a look. And I'm trying to think which one you are. Okay, let me think. I mistyped. Let me correct my here. Oh, we'll be fixing everything up. Does everyone have access to this channel? I think everyone has access. Okay. I think you're emailing. Okay, right, here we go. Let's take a look. GLM, and let me take it over here. Okay, GLM, X2 gender, number of drinks per week, favorite alcohol, because that's categorical. Great job right there. Data equals survey 11. Family equals binomial. Oh, and then store it into an object. And then don't delete off your G. Did it have a G beforehand? It did. I just deleted that. I was like, am I seeing things? Survey 11 not found. Load survey 11 data. Okay. Yeah, there we go. Let me check, see if everything... Is that what you're getting? Cool, so I'm trying to think. Is this Ben's right here? Let me look at who's I worked on. Okay, I worked on Uz. This is working right here. And favorite alcohol does... That's yours right there, Blake? Mm-hmm. Working fine. Working fine. Oh, this is so cool. You're predicting if someone's gender right here. And, oh, man, this is such a cool one. No one steal it. Blake, I'm throwing you... You thought it was garbage? This is a cool one, man. I like this. Let's take a look at this. And just think about your world. Like, I'm not saying this is true or not true. But people who drink what are the most likely to be men. And... which is funny because I do not fall into this category. I'm trying to think which one I fall into. I drink like wine coolers, so I'm like the least likely to be a man. And I drink like, I barely even drink one drink a week these weeks. Like if you ask me what's my favorite drink, I'd probably be like, I mean, it's literally gonna be like Mike's Hard Lemonade or Smirnoff Ice. Probably Mike's Hard Lemonade. Like they got like a black cherry one. Only drink if you're responsibly drinking and of age. And please Uber, Lyft. Even in COVID times, it's a billion times safer to Uber or Lyft than to get into a car even after 1 or 2 drinks. I literally used to think I'll have 1 drink and then drive. I'm just being real with everyone here. That's the most I would ever drink and then drive. And now I'm to the point where I'm just like, if I have a drink, I'm not driving. I've just become more against even having a drink and then driving. And we got some places we could walk to around here if we ever wanted to go out and eat. But especially when I lived near downtown Knoxville, it was really rare in the last 10 years where I lived at my apartment that we even went anywhere that I needed to drive to. If we, you know, but I would have the policy I could have like 1 glass of wine at dinner because I'm almost a 200-pound guy. And then, yeah, it's enough life advice with Brian, but personal views are If you're considering any drinking, maybe get a DD or a lift. Like, hey, let's have a night on the town. Let's get a lift and let's just go enjoy our night and maybe have 3 or 4 drinks. So we got that lift, we got that ride, and if the lift falls through, we always got a friend we can call or something because friends got our back. But when you look, oh, you're saying there's no sigmoidal shape? No, the sigmoidal shape exists. It might be hard to see. You can see it peeking across here. These all have a sigmoidal shape pretty well. Does that make sense, Blake? You forgot to put family binomial? Awesome. Got it fixed right there. What does everyone notice about this right here with your world? Like, just interpret this. 2 individuals who are otherwise identical, like they have the same number of drinks per week, but one person drinks beer and one person drinks wine. The person who drinks wine is what? At all points. You don't need to look at coefficients right here. You can just see it visually. The coefficient of wine is going to be negative. I can tell you that. The coefficient of wine is going to be negative. How do I know the coefficient of wine is negative? How did I know the coefficient of wine, which is right here, is negative? And you could say that, and this model does predict on the binomial. So you could say that because in this, there's only 2 levels, male, female. So it'd be technically, in just the way I talk statistically speaking, is I would say less likely to be male, like has a lower probability of being male, because we're predicting probability of male. So usually we put it in terms of the probability of the level of interest we're talking about, and the negative sign right there. Exactly. And it's below the black. Does that make sense to everybody? And does this make sense with your worldview? Like, it's so funny. Like, I would go and get drinks for Chelsea and I. She's obviously of age too, because I mean, I'm almost 40, so I'm getting old. But I'd be picking up some beer and like some wine coolers, and I'd always joke at the corner market. I'd be like, yeah, getting some beer for me and some wine cooler for my lady. And they'd be like, we know you, Brian. And they'd be like, yeah, you're right. And they'd be like, we got a new Mike's Hard Lemonade. I'm like, oh yeah. And they'd be like, oh yeah, go pick it up. And there's new nice Belgian beer for your lady. I'm like, yeah, she might like that. I'll go get that for her. Like, Brian, you're weird. You're crazy, man. But the model shows that if someone says they drink beer, even to any degree, they're a higher probability of being male than people who don't drink beer. Once again, this model is just what we see, what we see with the data. It doesn't mean things have to work this way. I obviously break the trend. She obviously breaks the trend. It's just probabilities. So is this making sense right here? Is this making sense with what you see? Also, 2 individuals who are otherwise identical, meaning they drink the same alcohol. The person who drinks more is more likely to be male, i.e. the person who has more drinks per week has a higher probability of being male. And you can see that right here, irregardless of what alcohol someone drinks. Someone's like, I drink 10 drinks a week. I don't know, just I'll space it out. I drink 20 drinks a week. It's a good bit. Well, the person who drinks more has a higher probability of being male, irregardless. We could make this really crazy right here, which don't do this quite yet. But whoa! So you see right here. Wait, if you don't have a favorite and you drink more, then it actually you have a higher probability of being female. The interaction right here is not statistically significant, probably due to low sample sizes. Even though you see a huge switch right here, probably that's a small group. To look at that, because I'm guessing that the none group is a very small, has a very small sample size. Hence why we're not getting it. Oh wait, no, it's number of drinks. Cook the wrong variable. No, it's 134. Well, I'm shocked it's not significant. There must be a lot of uncertainty in these estimates. I wouldn't create that model quite yet. And then the way in which favorite alcohol, or the way in which number of drinks explains the probability of being male, would depend on what alcohol someone drinks. If someone does not have a favorite alcohol, then as they drink more drinks per week, they have a higher probability of being not male, or they have a lower probability of being male. The strongest relationship right here, and we'd have to look at the summary right here to see this. The strongest relationship would be, oh my gosh, so much output. Let me expand. It's just that the variable names are very long. The strongest relationship is with beer. It did look to be the strongest. The black line is the strongest. The other lines are weaker because it starts out with a positive coefficient, and the other interactions right here just decrease the coefficient. So much so that none actually creates a negative relationship. And you can see that here from the original coefficient of number of drinks week being positive, and this coefficient would actually make it negative when you add together those coefficients. Okay, let's look at who else had a model they want me to look at. I'm going to cut the video right here. I think someone else who had other models. Really great stuff right there. Really great. Is this helping out, making sense of these logistics? Blake, did that help us seeing that? and being like, okay, that's how I analyze my model. That's what it means. This is what I'm looking at right here. Me, please, Trace. Yes, I think you're Triblu right on the. Let me go look at yours. All right, here is your file. Let's go take a look. Okay. Predicting whether or not smoking from father's race and father's weight. Let's go take a look. Let's hop in here. Let's do this. Okay. I was trying to set up quick buttons on these, and then my stream deck didn't want it. Can you explain on the strength of reference relationship? Yep. The strongest relationship here is going to be the steepest line. And this one's a tricky one. Just on your data right here. The original strength of the line is 0.07. So that's the original strength. And these other ones make it weaker, but not negative. And those are the red line. The liquor line's the red line. So the liquor line is going to have a strength of that. The original line has a strength of that. That's the black line. And the blue line, which you notice here is the wine line, has a weaker relationship. It actually has the weakest relationship. There's the black line, the red line, the blue line, but the green line, we take the original strength of number of drinks per week, and then we subtract from that the mega negative coefficient right here, super negative, and it actually becomes the strongest relationship because it is the most, it's the steepest line. It's hard to see via the graphic. You could kind of guess it's the steepest. But you can see blue is the weakest. There's the coefficient of the blue sigmoidal term. Here's the coefficient of the red sigmoidal term. Here's the coefficient of the black, which is the strongest positive. And then the strongest relationship right here would be the steepest line, even though it's negative. Right there, asking Ben, great job. It says survey love. Yep. Dylan right there, 20 points. Helping out. Vols help Vols right there. Thank you, Dylan. Dylan solving some problems. I bet that's the issue. So it's not really the slope anymore. It's the sigmoidal shape. You're on the right track with that, Blake. We wouldn't really call it the slope. It's the sigmoidal strength or shape because these are no longer lines. It's still where the coefficient of the slope would be. Like it's like where the coefficient slope estimates are, but it would be better described by like the sigmoidal shape or the degree to which we have a sigmoidal relationship or the coefficient of the sigmoidal relationship because it's no longer a line. Does that make sense? It'd be bad to call it a slope right here because it's no longer like a slope, like a y equals mx plus b type slope. Not the end of the world, but just like a terminology talking about right there. We'll take a look at traces right here. He's got a logistic fit. He's going to visualize it. I don't have the birth weight data set loaded up yet. I'm going to just space out the code a little bit here. I do like to try to make my code super purdy. And, oh, I just need to load one more thing. There we go. And here we, whoa. Don't worry, not the end of the world right here, but I can tell you what the coefficients of your model are. And I like that we're getting so many interesting things right here. And Blake, excellent work. Let me throw Blake another 20 points. Keep asking those questions, Blake. Like, just when you have a question, just throw it right out. Now, what's interesting is the coefficient, like, race of father might actually be statistically significant. But do you notice how, and just think about this. Just think about this for a moment. We're predicting the probability that the mother is smoking. So the probability that the mother is smoking, and we have the father's weight right here. I just want you to go logical on this. If you have two people where one person weighs more and one person weighs less, do you think that would tell you anything about their spouse smoking? So we're going to look at the father's weight here, where we have fathers who weigh like 200 pounds and fathers who weigh like 250 pounds. Now, it looks to be a little bit of a negative relationship, but the relationship looks super, 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 super weak because the lines look super, super flat. And we're predicting the probability that a mother is smoking now. Like, I guess she's like literally, while we're asking her the survey, just smoking cigarettes. There's two levels to this, smoking now and smoking never. Smoking now is the level of interest. And you would think maybe there's some sort of relationship. Like, funny enough, some people, I actually worked with two people. One person was one of the skinniest people I've ever known, and she smoked all the time. And the other person I worked with, he was like 6'5" or 6'6", probably weighed close to 300 pounds, like a heavier dude and a bigger dude. Like, this is one of those dudes, if he like pushed against a wall, you'd be like, I don't know if that wall is gonna fall or not, because he was a strong guy, and you're just like, whoa. And he smoked even more. So, I mean, which one is it? Do you smoke when you're light and you're just using it as appetite suppressant almost? Or do you smoke when you're big and you're a big guy and you smoke a ton? Or what is it? I don't know. Interestingly enough, the p-value on this, and you see the father's race comes back with a significant p-value, but I can bet you good money that father's weight, due to the flatness of those lines, father's weight, when we look at this model, I would bet good money father's weight, yeah. What was I noticing right here immediately that my eyes were drawn to because the lines are flat? It looks like the what model, which that model would have the highest possible p-value. Which is all right. This is fine. This is what we'll see sometimes when we do logistic, and we need to know to look for this. You should have an eye for these things eventually to say like, oh, that's a super high p-value. That looks like the blank model. Or it should look like the blank model, which those do look like the blank model. What do all those lines look like? I could show you some cool stuff right here. Because let's go ahead and subset on, let's say, individuals who are, let's go right here and go with Asian. So Asian is first because it's the reference level. Let's go to subset and EX6. Which one is this? EX9. EX9 birth weight on father race. Where was it at? Father race equals Asian. Okay. So this will create, and let's just call it sub. And what percent of the Asian fathers do you think are smoking now? What percent of the Asian fathers would you guess are smoking now? If anyone can get this within 2%, I'll throw 50 points. So if we go here to table, divide by n row, sub. If anyone can get this within 2%, I'll throw 50 points. What percent of Asian fathers out of all of them do you think are smoking now? What percent out of Asian fathers do you think are smoking now? And we're just doing it because it's the reference level, which is the black line right there, just right there under my nose. And hint, the reference level, and we can see it's a flat line, is going to be the naive model for that group. Yeah, probably 20% right there. So let's take a look. You're within 1%. 21 should have went with that, but no, you got it. That's, I would have guessed 20% also. Yeah. And that's because I said 50 points, right? So is this making sense how I'm talking about these things and why I'm saying, oh, this behind me right here is basically the naive model for the Asian group. It's a flat line. Now there is a negative coefficient with father's weight, but it's really not statistically significant. So we're just seeing these basically naive models, which would be for all Asian fathers, the probability of smoking now is about 20%, and it really doesn't change much from the naive. There is a decrease in probability as father weight increases, but this decrease in probability is not statistically significant right now. As in, two fathers who are otherwise identical, and we're predicting the probability the mother smokes now, excuse me. So here we go. Two fathers who are otherwise identical, but differ in their weight by 1 pound. The father who is heavier is less likely to be smoking now because there's a negative coefficient right here on this. Two fathers who are otherwise identical but differ in their weight by 1 pound. The father who weighs more is less likely to be smoking now. Negative coefficient, less likely. Two fathers who are otherwise identical, but one is Asian and the other is white. And the white individuals actually have the highest probability of smoking. So, and this is statistically significant. If we look at the drop one on your model right here, can we go over forward making a prediction? Yeah, let's look at that next here. It's very similar. So, oh, I got to do the test equals chi-squared. Has to be in quotes. I did this wrong 2 times today. Yeah, father's race is super significant. Two fathers who are identical, different weight by 1 pound are expected difference. But not the expected difference smoking. The one who weighs more is what likely. So remember, it's always probability with this. The one There's an issue at the end. Two fathers that are otherwise identical but differ in weight by 1 pound. The father who weighs more is what likely to be a smoker now, or for the mother. It's just so weird because this variable is if the mother is smoking. So two fathers who are otherwise identical but differ in weight by 1 pound. The one who is heavier is more likely to have a pregnant wife, or I mean, it's less likely to have because it's less likely, negative coefficient, less likely to have a pregnant wife who is smoking now. Let me repeat that. Two fathers who differ in their weight by 1 pound. The father who is heavier is less likely to have a pregnant wife that is smoking now. The father who is heavier is less likely to have a pregnant wife that is smoking now. This one right here, which is the highest coefficient, whether the higher father weight is expected to have a lower probability of a pregnant wife. Where the person who has where the father who is heavier is less likely to have a wife who is smoking now. It's such a weird one, because we're talking about it's just a very weird model. But no, don't worry, that's perfectly fine. Just make sure to get it right. With this right here, two fathers who are otherwise identical, but one is Asian and one is white. The father who is white is more likely to have a pregnant wife who is smoking now. And you can see this right here with the black and the blue line, or the light blue line, the teal line, I guess that would be. So we have the Asian line right here. We have maybe two fathers who are the same weight, i.e. they both are 150 pounds. And so you got an Asian father who's 150 and a white father who's 150. They're otherwise identical, have the same weight. So two fathers who are otherwise identical, but one is Asian and one is white. The individual, the father who is white, is more likely to have a pregnant spouse who is smoking now. But everyone still, we would predict, doesn't have a spouse smoking now, even though there's a higher probability. Is that making sense for your Trace? Rather interesting model. Because it's weird because you're talking about the father to then talk about the pregnant wife and whether the pregnant wife is smoking now or not. Hopefully that's making sense right here. You know what I might do is I might switch back for number 4. Is the model making sense? We'll go down to number 4 right here and we'll do that next. And I might switch back to the previous model. What is the probability the individual is the level of interest? Yep. Make a prediction for a new individual and solve the following. Let's go take a look at that right here. Let's take a look at number 4. 2 seconds. Let's go back to that. Okay, we're going to look at number 4 right here with making predictions with logistic models. This is something we talked about in class today. We can also do it with the code. You can solve it out by hand. We did a lot of solving by hand today. Or you can solve it out with the predict function, which makes life way easier. Let's look at that. So I'm going to switch back over to our previous model with the number of drinks per week and stuff. And let's take a look at this model right here. Now, whenever you're looking at your model, you want to see if your probabilities are coming out correctly. I'm going to solve for my own model right here and figure out the probability of me being male. Let's figure out the probability of that. And you see right here, and I've got a different model in, so let me go grab my model and switch it up. Might be easier if I type it out. You can cycle through old commands here by doing this. I'm just going to grab this command. I'm going to remove the interaction. And now we have the model you currently see on the screen. A good way to check that is to go right here. So this is the model on the screen, and let's think about it. Now, if you were to write out this model as lines, it would look the following way. We're going to get right here probability, or rather logit, of male, which it will solve for that. It's the logit of male is equal to the intercept plus, and then we'll just say drinks. We need to decrease font size. Where'd it go? Really? So the drinks right here, and then we need to go, this is liquor, minus this times, oh my god, sure. Liquor, sure. And then minus this times none. I'm just algorithmically going through, and then minus this times wine. Does it make sense how I was able to write this equation? I'm going to try to make it nice and big here so everyone can see it. Does it make sense how I took this output right here on the screen and was able to write this equation right here. Let's make it look a little bit nicer by deleting down some decimals. Of course, I would carry them as I do this. Like I'm going to carry decimals as I solve this. Also, R will do it. But good, that does make sense right here. I'm glad it does, people, how I'm able to write this equation right here, that the logit of male is equal to the intercept plus the coefficient of num drinks per week times this. Now, what are the only values that liquor, none, and wine can take on? And you can see right here how they are written. What are the only values of liquor, wine, and none that it can take on? So we can actually solve this ourselves. And then I'll solve it using R here in a moment. What are the only values that liquor, none, and wine can take on? What are the only values? 0 or 1. So what I'm going to do right here is I'm going to take my equation, and this is one way to solve it. And you can actually use the equal sign. You got to be careful, though, because we don't have values for this. I'm just going to call this L male for logit male right here. And you can use the equals. It's the same thing as the store into. And I want to store here drinks is equal to, I'm lucky if I get 2 drinks this week. That's probably a good thing. Liquor, we'll store 0 for that. None, we'll store 0 for that. Wine, we'll store 0. We'll store 1 for this. Okay. So now when I solve this, we have just solved out and obtained a value of the following. I want you to look at this graphic and tell me what you think Brian's probability of being male is. I want you to take a guess and tell me what you think. Here's Brian's answers to the question on his drinks. Here's Brian's answers to his question on liquor, none, or wine. So I want you to think about it. What would you guess Brian's probability is? And this is what the equation solves to. This is where people make the mistake. What do you think Brian's probability is? And here's a way to check your answer. The answer to my logit is this. Now you can go ahead and solve it. Like, if you know how to solve with the logit and what we do with the logit, then you can solve that right there. But so we don't, the logit just, I know things about it. I know the probability is going to be less than 50%. I don't know if I could have told you much more. If you told me logit is negative 1.67, I'd be like, okay, it's less than 50%. It's going to be not the level of interest. But just look over here at this graphic. Remember, we're at 2 drinks. Well, it wouldn't be 0. We're at 2 drinks, and Brian said his favorite alcohol is what? So what do you think the probability is going to be about? Like, what should we about get when we solve this properly here? When we produce a probability, probabilities should be between 0 and 1, or 0 and 100 if we multiply it by 100. So the probability here, any guesses of what it might be? So if I take this and I solve it through our formula, e to the value over 1 plus e to the value, about 0.2, maybe a little bit less, like 0.188, I say. We might not have carried enough decimals due to my deletion of decimals. Maybe that's right. A little bit less, yeah. It's lower than I thought. It's saying about 16%. Let's have R solve it for us, and this is how to have R solve it. We need to do the same practice we've been doing if we want R to solve it. We need to make a data frame, and we need to bring over our variable names. We've got right here number of drinks per week, and we need to set number of drinks per week equal to the amount we want. And then we need to set favorite alcohol equal to what we want right here. And it was wine. So now we have a data frame that looks like the following. The data frame just has in it the X variables that are going to make predictions. So now we can go here to predict using our model, new data equals, and we go to df. And guess what we get? This is all the decimals carried. Now that's not the answer again, that's the logit. So if I take all the decimals carried and we don't do extra things, we now get a probability of almost exactly 16%. So my rounding was not that big of a deal. If we zoom in on this, it should be very close to 16%. And that might, yeah, should be about 16%. I think if we do this, though, there's a way, and I forget, there's a lot of commands to remember. Where is it? Does anyone know? I'm gonna have to Google it. Can we go number 3? Yep. Definitely, Trace, you got it. Let me see. Okay. There's an argument I'm missing and I always forget it. And the predict function is so weird to me sometimes. Type response. There it is. I wish it said, oh, look, it literally says it right here. Like, I wish it said that. There it is. Yeah. So if you do that right there, it'll give you the, so it was telling me. Can we go over confusion? You bet. So this will actually output the value right here using the data frame for the new individual. You can actually get it. So we basically did it 2 ways right here. We solved it by hand, and then we solved it using R. And then probability not the level of interest. I'll let you think that one over. It shouldn't be too crazy. But someone is either the level of interest or they are not the level of interest. Let's go do number 3. Okay, so number 3. Number 3 is run the check regression. Let's go look at that check regression. So looking at the check regression right here, what's the deal with check regression? Check regression is basically going to tell us if the sigmoidal curve is a good idea. And I like it. Now, it does use randomness, so you don't get the same results every time. But it's literally asking, is the sigmoidal curve a good idea? What's the answer? I mean, we got 2 checks right here. How's it breaking, Dylan? So we're basically asking, oh, and someone might have an interest. Oh, I wouldn't probably do. I know why yours might be crazier on this one. Yeah, you're doing, no, we're predicting probability male, so we're good. Sorry, my brain broke. So what's this telling us right here? When we do check regressions, what is the high p-value telling us? When we do check regressions, what are these high p-values? I wouldn't take the mean of it. It's 2 friends, basically. It's just 2 friends. And your 2 friends are talking to you. And sometimes one of your friends will tell you it's a bad idea. Sometimes one of your friends will tell you it's a good idea. And in that instance, it's hard to tell what to do. This friend says, no, don't do it. This friend says, yeah, it's fine. And then you're like, well, I don't know. And then a high p-value, as you're saying right there, Trace, you're exactly right, means the logistic curve is a good fit for our data. Like, we are literally asking, is the logistic curve a good idea? High p-value means the results we see are expected to be seen given the logistic curve is a good fit. Low p-value means the results we see are not what we would expect to see if the logistic curve is a good fit. Like 200 lines of warning in the chi-squared new sample chi-squared approximation may be incorrect. Suppress warnings. And then they also have me take a look at it too. A good way to remove that is to throw in a little bit of suppress warnings. So those are warning. You can suppress messages. You can suppress warnings to be like, I don't want to see that. And then if I were to put in here warning, hello, it's going to like stop that from printing. But this should print out a warning message. It doesn't want to do it. That's meant to be in a function. So your function, print warning, and it doesn't take anything. Prints this, run it. And then if we run print warning, then that won't do anything there. But if we run print warning here, it'll really return. My brain is breaking today. Let's put here message. Hello. Unless we suppress messages. There we go. That suppresses it. So now it's print message. So you should be able to suppress warnings or suppress messages. Don't know why my thing didn't do what it was doing. I don't know. When you print out the confusing major, are you supposed to just get 1 column? You could. Something, oh, and yours will, Trace, because yours is the naive model. So yours, great question right there, Trace, and then we'll go to some confused. So hopefully everyone knows how to do the check regression. Please ask questions if you're stuck on it. So Trace, it looks like yours is giving you the naive model. I'm going to pull up the notes here so we can kind of look at that and look at your model is looking like your confusion matrix is looking like this right here because your confusion matrix is the naive model and all your values are going to be in actual never. Smoking now is going to have more actual now, and you're going to get predicted never for everyone. Your predicted never is going to be here because all your lines, if you look at the way the model looked, all of your lines were completely flat. So when you think about how the model makes predictions, everybody's going to be predicted to be smoking never, which is the not level of interest. So all the probabilities right here come back below 50%. So that means your model is going to make predictions that it's going to be predicted never. And then you'll see what percent are smoking now. So interestingly enough, your model's metrics, so this is kind of a good quick answer. Your model performs exactly the same as the naive, which even though you might have some statistical significance here, especially with father's race, your model just has no real practical significance. Does that make sense, Trace? Your model is like, yeah, there's some variation due to father's race. Like we see it helps us out, creates differences between these lines, or sigmoidal curves, rather, I should say. They look like lines. Why would my code be returning those chi-squared approximations may be incorrect? Small sample sizes. Which data set are you working with, Dylan? Small sample sizes will do that because it creates issues with the estimates when you have very, very small sample sizes. These are excellent questions. And I really like, we did a little change up of how the assignments were done. I think people are asking some amazing questions here. Let's look at the classification rate of the drinking model right here. And so here's our model on people's amount of drinks per week. I think this is an awesome model right here. Yeah, it might be that some of the groups have a very small sample size, Dylan. You email me the RMD? Awesome. Here, I'll try to take a look at that next. I think I'm doing the STET one here one soon. Let's look at a confusion matrix on this. Okay. So what will the naive model predict? And I'm going to zoom this in really big right here. What will the naive model predict for everybody? What will the naive model predict for everybody? Hint, the naive model only looks at... So what will the naive model pick? There's some Jerry right there, assignment 1 through 20. Or 475. I can't even think. What will the naive model predict for everybody? I said predict, but I mean, it's a trick word in there. The naive model doesn't know any about that. What would the naive model predict for everybody right here? And then how many would it get wrong? So what will the naive model will predict everyone is female because the majority level is female. So you go to the total columns right here and you only focus on this for the naive model. So the naive model knows most people are female. So the naive model says, well, if most people are female, everyone's female. Does that make sense? It's not literally saying that's true, but it's like, well, I have the greatest probability of being correct if I predict someone's female. So you would get the misclassification rate of this right here, which I think we're talking about misclassification rate in this. So the naive model itself, when it predicts everyone is female, would be wrong 45% of the time, would be right 55% of the time. It classifies people correct about 55% of the time. It classifies people incorrect about 45% of the time. When you look at your model, you need to look at based on the on diagonal. These are the correct predictions where somebody was predicted female and they're actually female. And the correct prediction here is when somebody was predicted male and that person is also actually male. Wow, that actually kind of worked. So these are the correct ones. This would be the classification of your model, how often your model gets things correct. And your model is going to correctly classify things, the sum of these divided by the total. So we just figure out, that's not how we add things. We figure out right here how many total your model got correct out of the amount that exists, and that is the accuracy of your model or classification rate. Like, how accurate was my model? It accurately predicted somebody being male or female 67.67% of the time, and then it was wrong 32.32% of the time. So you would do a comparison right here to look at how much better your model does. And you know, this model is pretty good right here. It's not too bad. You know, if you ask someone, you know, I think the previous we dropped from like 45% accuracy or misclassification to 32%. You can come up with some rather interesting models right here. The thing is if you throw in like one more variable, you can get a really crazy good model. All you need to make this model absolutely insane and have a way better ability to predict is, let's go right here. Let's grab our model again and watch this. You throw in a few more variables. We could do variable selection. We didn't get to that, but that's all right. I'm guessing if I just add on to this, let me attach it. Attach. Just look at this real quick. I think we got to head over to the other video. Cool. Weight. Oh no. EX, gender, height. There's it. Well, it might not be in the same data frame. I don't know if that did it. Confusion matrix. Yeah, now the model does way better. I hate that it does that. Goes all those extra spaces. Now the model misses by about 13%. Because, I mean, just think. All you're doing is you're adding on somebody's height, their weight. We'd have to look at survey 11 to see what else is in here, but I bet there's other variables. And there's ways of doing variable selection. Are you satisfied with your weight? That might even help more. We've gone away from being able to visualize this now. Did that help? Might not have helped. 33. Error in survey 11, non-numeric argument to binary operator. So it's actually mad about that variable. I'd have to take a look at that. Your class, your GPA. So, am I in the wrong survey? Might be the issue. Too many variables. Was it still getting the same argument? Is it? I must be in the wrong survey. Am I going mad? Oh, data equals. What am I doing? Hopefully someone noticed that besides me. Wasn't there satisfied with weight? There we go. Okay, last variable here. Yeah, we're dropping. We'd have to look at this right here and see how it does. We might be overfitting the model. I don't know. But at this point, our misclassification rate is going to be less than 10%. So we're doing a better and better job at classifying people accurately by taking in more X variables. We might also have a problem with overfitting our model. But is this making sense right here, how to look at the confusion matrix and realize that these are the people here on the off diagonal, the people we are classifying incorrectly. Like these are 25 individuals here predicted to be male who are actually female. These are 36 individuals here who are predicted to be female who are actually male. And adding together the two and dividing by the total will give us the percent misclassified. If we want to get the accuracy of the model, we can just take the complement of this to find out the accuracy, which is just going to be, we're wrong about 10% of the time, we're right about 90% of the time. So hopefully that's making sense. Any last questions right here? I think, let me look at when my 201 thing is. Today is a busy day. Thank you for everyone who's watching and who's liked the video. We've got a lot of watches. We still got a little bit of time. We'll see if we have more things. I think it said something like, how many people have liked this? 7 people have liked this. Thank you so much. I really appreciate that. What will we go over test in class? No, like we all have covered everything that's like, there is some interactions on the test. Just tomorrow, we're just going to review. We're going to take questions. We're going to talk about the test. You know, we're going to do the Kahoot tonight, but we're just going to review. Like there's not going to be, we're not going to go into new material. We're not going to be like, hey, let's start up another thing right here. Let's go into model building and let's do this and this, which there's one question that makes me think that there's actually one question. I mean, it shows you the answer. It's AIC, which we have seen AIC, but we didn't really talk about AIC. It's a super important topic, and I wish we could go more into it, but we didn't get the chance. AIC is how close a model is to the truth. We didn't get the chance to talk about it with model building. So you did see AIC. If you ever looked at the choose order code, you would see it. Did I not save? Oh, because we got another variable. Figure too large. Is the fit of the data with how close it is to the truth? Exactly. It's how close our model is to the truth. And you can see the AIC right here being measured. A lot of times your best R squared adjusted is oftentimes, if you notice using our rules, yeah, and I have to make sure that's not on the test because, of course, I was like waiting to finalize everything on the test till we finish today to make sure, because usually I have like, like a little bit of time. Usually there's a little bit of time between the end of the semester and the final. So for me, even it's like, okay, I got to be getting everything done. I'm not going to put AIC on the test. I just don't want to do it. It is on the review. I think that's because it shows you the answer. So I don't think that's too crazy. But you notice right here, AIC, which AICC is just a version of Akaike's information criteria. Dr. Bosselgan told me how to say it properly. Say Dr. Akaike's name properly. And it actually usually converges with our standard, which is rather interesting. Dr. Petrie's standard oftentimes matches Akaike's information criteria. You could keep it. It's on the practice review test. I guess. I mean, I'm 50-50 because I wouldn't want someone to be like, wait a minute, we didn't cover that. And I'll be like, it was on the practice. They'll be like, but I didn't do the practice either. I'm like, no, it's a free question. It's just how close our model is to the truth. The lower it is, the better. And it can go negative infinity. And it's basically based off of how good our sums of squared error is. Like we want the most reduction in sums of squared error at the cost of the least variables. It works off. Definitely, we'll look at some bonus points. I'm definitely going to put some bonus on the test. I think the test should be pretty fair. It's a little bit tough. The written questions are probably the hardest part of it. So he'll break into Tom a little bit of test here. It's chill music. So talking about the test, when it comes to the test, the written questions are going to be the toughest part. I feel like I should plug in my phone. The written questions are going to be the toughest part. I can see a lot of people losing points on those. If you don't know your interpretations, like if you have no idea how to interpret stuff, not good. That's where points are going to get lost because there's just separate interpretations for different things. You have to know how to interpret when Y is quantitative, when Y is categorical. You have to know how to interpret when X is quantitative, when X is categorical. Just the big things right there. And you just basically got all the different combos. Like if Y is categorical, you're talking about probabilities of Y. If X is categorical, you have to compare reference to indicator. So is this making sense? Who feels a little bit okay about interpretations? Because we do a lot of those in class. We practice interpretations a lot to make sure we know what we're seeing and we can look at a graphic and kind of explain it off to someone. Like that's my goal, is like you can interpret these things and make it make sense to someone. And I read some interpretations and I'm like, no, it scares me. We give it some template during the, yeah, we can definitely do that. We can go over tonight. We'll go over and we'll write some template interpretations. I'll make no errors. Thank you everyone for being so positive throughout. It's just so quick. Like, I love teaching and man, I'm just like, wow, you guys are doing excellent. You're keeping up. As long as there's no trickery. I don't think so. I'm not trying to put some trickery in here. Trying to keep it as straightforward and like, here's a variable. Here's what the model's predicting. You can see the code. It tells you what it is. We're predicting whether somebody is satisfied with their weight, yes or no. We're predicting whether or not somebody's pregnant, yes or no. We're predicting whether or not someone has diabetes, yes or no. So it should be pretty straightforward. And then I'll be going in and grading these. So tomorrow after I do my, do my dentist thing, I can't even think of what it's called. But what's funny is the weekend, Saturday morning, my tooth was hurting. Today it really hasn't hurt. So what's up with that? For like a whole week, I was like, last week I was in pain a lot. It sucked. And then, I guess that's just the way things go. I mean, I think I have pretty good teeth. It's actually like, you can't see it. Go this way. You can't see it. It's like one of my back teeth right there. And I'm like, I probably got a cavity. I thought, good teeth. Try to keep them clean. I try, brush twice a day, floss, use good mouthwash. I might have just like hit my gum too hard and like got a slight gum infection or something. I don't know. Just random happens. So I was like, probably a good time to see a dentist. Get some x-rays done, figure out if any teeth need drilling. That'll be fun. It's just so weird. I don't like getting older. Body starts saying no. Any last questions here before we head off and Brian talks about all his dental mishaps? I try. My one tooth keeps coming forward. I need to get like Invisalign. As I get older, that tooth's like, I'm gonna escape your mouth. Like, what are you doing, tooth? Go back. Hang out with the other teeth. Well, great work, everybody. We'll be back here in a little bit. I'm going to be streaming for 201, and we're going to go over their project. And then we'll be streaming for Kahoot. Then we're going to work out. Then we're going to get some groceries. Then we're going to go to bed. Real fast, you said it doesn't matter if you're getting the chi-squares. Yeah, and I'll respond to that email here probably in a little bit. You should be good. Just delete or suppress the errors. Suppress the errors, and you should be pretty good. Just be like, no errors. It's probably due to small sample size. It's a concern of sorts. It's calling your attention. When will the test go live tonight? Midnight. I'll be finishing things up. Maybe closer to 1 a.m. My goal is midnight, but I'll be finishing things up, making sure it's right. Midnight, 1 a.m. Goal is midnight. But with oh man. And they'll be grading assignments tomorrow. And then, man, I'm glad we got 4th of July coming up. We get Monday off, which isn't even 4th of July. It's 5th of July. But I'll take it. I'll take Monday off. And just relax. Get a 3-day weekend. But we're starting off easier, first day of class in 474, 475, a little bit easier. We do break into some material. And I've been trying to develop some more stuff right here. Just a lot going on. But you got this. We got this. Stay strong. We got 4th of July and 5th of July weekend coming up. I just got some burgers today. Burgers and buns. Gonna eat some burgers this weekend. Enjoy your time. We'll be back here in a little bit. I'll see everyone later for now. Enjoy the weekend. Have a good time. But work hard. Make it to that weekend. And then just relax. Bye for now, everyone. Bye.